Okay. First question is, are there any questions about the homework simulation problem? Okay, we're ready to start now. So I'll start again. Are there any questions about the homework problem, the simulation? Okay.
When I use a very small negative number, for instance, I use -1.5. The forward, average forward, and it's not equal to the average backward.
Well, the reason that
Others are equal. I mean, the T point, okay, backward and forward, there are two parts.
the backward and the forward recurrence times will be equal in the limit as t goes to infinity. But if t is finite, then there's a bound on it, because obviously the backward recurrence time can't be greater than t. However, t is so large that that really shouldn't have an effect. It appears that the theory, of course, predicts this strange behavior that as the inter-arrival times gets larger at first, the waiting time until the next renewal actually gets smaller. So you have a minimum. So that's very surprising. On the other hand, I'm not sure from what I'm hearing that the simulation bears that out. The simulation may not contradict it, but it also may not support it either, because there may be too much noise in the random number generator or in the accuracy of the random number generator or the length of the run. So if you can make the simulation more accurate by running it longer or using a better random number generator, then do it if you can. But maybe this might either confirm that the theoretical effect is real, because it won't deny it. It may just make it so that you can't tell. But if you can't tell, then it shows you the difficulties with simulation. And its simulation is not too accurate. And especially, it would be very difficult to determine counterintuitive effects if they're small by simulation, because if you weren't looking for them, then there would be no reason to think that they were there.
But for larger U, those two are equal. I don't know why.
For larger U.
For instance, I use U equal to 1.5. Those two are much different. But I use -1. They are almost the same.
I don't know. I don't know the answer.
I tried several times. It's 100,000 iteration.
Yeah? Okay.
And I tried large T. I couldn't get it.
I don't know the answer. Just play around with it, and whatever you conclude, let me know. Okay, so go ahead.
If you change t, when u is 1.5, the simulation will be very similar. If you change t, it becomes very triggers.
You mean the backward and the forward?
No.
The forward, I get a very good result for all the.
Do you get the minimum? Do you show that it minimizes?
Yes.
You get that?
I got the
Okay.
result. Very, very good. I just wondering, according to the theory, the forward and the backward should be, the average should be the same.
In fact, the distribution should be the same.
Yes, I use the same distribution.
Right. But I mean, the distribution function of forward recurrence time and backward recurrence time are equal, even though the forward recurrence time and the backward recurrence time are not independent of each other in general. Nevertheless, in distribution, they should be equal in the limit as the t goes to infinity. Well, the bottom line here, I think, is that once you're sure that your simulation logic is correct, and this case is very simple, then it's just a matter of playing with it to figure out what's going on. And if you can use a more accurate random number generator, or if you can run it for more replications, then fine. Just whatever it is you do and whatever experiments you run, whatever conclusions you reach, just write them down so I know. Because I'm interested in the results too, and I want to gather information about this so that I can hone it, so to speak, for future assignments. Also, it'll turn out that this will be related to a later assignment in this course, when it turns out that the same effect is there, but even less obvious than it should be. But you'll see it's the same thing. So what you're doing now is actually you're doing this homework plus a future homework. Now, as far as this homework goes, I didn't give a due date. So let me give one today. Let's make it due a week from today. Unless, I mean, everybody seems to be up on it now, not have any problems. So a week from today, unless you raise some further issues.
In this homework, we ask us to analyze the reasons why the minimum is not at the smallest number of you or not.
Well, I didn't ask it explicitly. In fact, what I did, although I sort of gave it away by telling you, is it's given away in effect by the title of the homework, what's going on here, because it should be very surprising. So my view at first was to let you discover it by saying, hey, wait a minute, what's happening? Why should there be a minimum? Now, the next question is, which you're raising, is why is that true? And there are two answers to that. One answer is, well, we did a mathematical analysis and we got a formula, and the formula shows it. So it must be true, unless you made a mistake in the mathematics, which of course we didn't. And the simulation is supposed to support that and say, yeah, it really is true. The second answer is, can you give an intuitive reason, a qualitative reason, so that you could explain it to someone without mathematics, saying why this is true? That's more difficult.
I use an approach to directly derive the probability. Since there are two competing aspects, one is the average
Right.
interval time, and another is the probability the t falls in which one.
Yes, that's correct.
I got use this approach to derive a formula which agree with the one we used.
Good,
In
great.
this formula, we can clearly see why the minimum is not at the smallest.
That's fine. That's very good.
Yeah.
Okay, I'll be interested in seeing that. Now, I said that there was that this effect actually appears in other places, but is sort of masked because here there's no queuing. Here the effect has been isolated purely, but in later case we'll see a model in which it's not apparent why it's there, but it'll be there for the same reason. And maybe your explanation will be helpful there. And I have been working with some colleagues on a study of certain kinds of models in which this stuff appears. And we've discovered some very interesting behavior. This is an example of it. Actually, all the behavior we've discovered at bottom comes back to this so-called variance paradox. But if you can come up with a good intuitive explanation, better than what we have, that would be great. We've included in one of our papers, which is under review, an explanation for this. And in fact, in another context, in another setting, this effect has been discovered and is quite controversial at the moment. People trying to figure out whether it really means anything. And it's funny with these technical questions that there can be a lot of personal hostility involved and people take stands as to which side they're on. So any interpretation or addition, anything you can add to this homework is great. That's wonderful. That's what I'd like to see.
For the service time and the customer arrival time, can we use one random function or two different random variable?
If you use the same random number generator to generate the same random number, to generate two different random variables in the same problem, then those random variables are not going to be independent anymore. Mm-hmm. And in fact, sometimes I have some problems that I give in which the premise of the problem is that a clever student decides to make his simulation run faster by using one random number for both random variables without recognizing that there's going to be a dependence, and then ask the student to figure out what the answer would be to predict what the simulation is going to produce. And this requires the student to think and understand something rather than to apply a formula about independent random variables, which doesn't apply anymore. For example, I could say, suppose I wanted to demonstrate the idea of convolution. So I could give the students two random variables that are independent, x and y, and tell them to simulate them, add them up, and then calculate the probability that the sum is less than a certain number. And then I could ask them to take the convolution of those things and compare the theory with the simulation. It's a straightforward, dumb exercise. But then I could give them the same problem, except that the x and y in the sum, instead of being generated with different random numbers, are generated with the same random numbers. So then the convolution formula wouldn't apply anymore because these random variables would no longer be independent. And the simulation will actually give answers that are different from what you would get if you assume independence. And of course, most of the students get blown away because they have no understanding whatever at the undergraduate level of what they're doing. They're just applying a formula. But the one or two students that understand what the formula means and then can adapt it to this case where with this dependence, that means that they really do understand it, so they get a higher grade. That's the theory behind it anyhow. Anyhow, the answer to your question, I think, is that you should not use the same random number in generating two random variables that are supposed to be independent, because then they won't be. Okay, anything else? All right, so we're basically at the heart of the course now, talking about MG1. And what I did last time was we went through the complete derivation of the generating function of the departure distribution in MG1. So what we did is we imagined that we have these an MG1Q, and these are the service completion epochs. And we let pi j star be the probability that in equilibrium, a departing customer, that's what the star is, leaves behind j other customers. And we wrote equations which were called embedded Markov chain equations, because we embedded the equations for these probabilities at different points in time at the service completion points. And so that let us change a process in a continuum into a discrete process. And then we analyzed that, and we took the equations for the embedded Markov chain, and we formed the generating function, which by definition is obtained by multiplying the probability with the subscript j by z to the j power and summing over j. And the result that we got after we did all of this work was z minus 1 times eta. Well, first let me write it as h. Z minus 1 times h of z divided by z minus h of z times 1 minus rho, where h of z was the generating function of the number of customers that arrived during a service time. Okay, so if we imagine that we have a service time, so here's our service time, an arbitrary service time. And during that service time, we have Poisson arrivals. Then h of z is the generating function of the number of arrivals that occur according to a Poisson process during an arbitrary service time. But then we saw that we could also write this way. I could say that I can use the relationship between the generating function of the number of arrivals that occurs during a random interval according to a Poisson process and the Laplace-Dietrich transform of the length of that interval. And if we call the Laplace-Dietrich transform of the service time distribution function eta, then the relationship is h of z equals eta of lambda minus lambda z. So with that, we can rewrite this equation as z minus 1 eta of lambda minus lambda z divided by z minus eta of lambda minus lambda z times 1 minus rho, where rho, of course, is the utilization of the server and is assumed to be less than 1. And this is equation 812 in the textbook. And that's basically where we quit last time. Now, if I differentiate this and set z equal to 1, then I would get the expected value of the number left behind. Of course, we know that the number left behind by a departing customer is the same as in distribution as the number found by an arriving customer. And we know that by Pasta, that's the same as the number seen by an outside observer. So this generating function not only generates the pi stars, but it also generates the pi's, and it also generates the p's in this case. And actually, it's remarkable that it's very easy to calculate these things. That's how we did it, but it's very hard to calculate these things and these things directly. Although, maybe I'll do it later on as an example. In any event, if I differentiate this and set z equal to 1, then I would have the expected value of that distribution, which would be the average number in system. And the average number in system is the same. Here's the answer that I would get. It's an exercise to do it. The average number in the system is equal to the average number in the server, which is the utilization or the carried load for the case of one server. So this is the average number in service. So the remaining part must be the average number in Q. And that turns out to be rho squared times 2, 1 minus rho, times 1 plus sigma squared over tau squared. This is equation 836. Now, the sigma squared is, by definition, the variance of the service times. And it comes about because when I differentiate this, I'm going to get a derivative of this. And then when I plug in z equals 1, I'm going to get indeterminacy. The numerator and denominator will both be 0, so I have to apply L'Hopital's rule. And when I do that, that's going to give me a second derivative. And the second derivative then is when I set the argument equal to 1 is where the variance comes from. And you recognize this term here as essentially the forward recurrence time. And so you can see that the forward recurrence time appears in this answer in a very important and simple way. This answer tells you a lot. For example, it tells you that the average number in system, or average Q length, so this whole thing right here is average Q length, it tells you that the average Q length depends on the variability of the service times. And it's going to be a minimum, all other things being equal, when the service times are constant, because then sigma squared will be 0. And when you have the MM1 case, sigma squared equals tau squared, and this piece right here becomes a 1, so that becomes a 2, that cancels with that 2. And so you can see that in the case of exponential service times, since this factor is 2, with constant service times it's 1, what that means is that all other things being equal, with the same server utilization, the average Q length is twice as long if I have exponential service times than if I have constant service times. And of course, sigma squared can be greater than tau squared. So in effect, for any row, for any particular utilization, you can have an average Q length arbitrarily long if the variance is big enough. So that's somewhat rather surprising. Now, using L equals lambda W, I can get the following. Let's just look at this piece here. Well, if L is the average number in system, if I take the system to be just the Q, then this piece here is L, which means that if I divide this piece by W, I would get, by lambda, I would get the average W, which is the average waiting time on the Q. So L equals lambda W then implies that the expected value of the waiting time is what I would get if I simply divide this by lambda. So if I divide this by lambda, then since rho is equal to lambda times tau, then dividing by lambda in the numerator would give me a rho times tau. So I would get rho times tau divided by 2 times 1 minus rho times 1 plus sigma squared over tau squared. So this is a very important result. We've already seen this. That's the formula for the average waiting time in MG1. Now notice that no assumption was made in this derivation of the order of service. The only requirement was that I be able to write the equations for the embedded Markov chain, which implicitly assumes that whenever the server becomes idle, if there's a customer waiting, then a customer enters the server, and that customer is statistically identical to all the other customers. That is a typical customer. And as long as the selection of the customer to enter service does not is typical, does not depend on, say, the number waiting or the required service times or things like that. As long as that's true, then this formula is true. This is true, and this is true, which means that it's not only true for FIFO service, but it's also true for LIFO, last in, first out. It's true for service in random order. So it's true for every case in which whenever a customer is selected from the queue, that customer is a typical customer in terms of his required service time. Now what I want to do is I want to derive the distribution of W, except that now I'm going to have to make an additional assumption, namely that I have service in order of arrival, a FIFO service. And then we'll get the standard Polytek-Kinchin formula, the Laplace-Dirichlet transform of the distribution function of this W. If we differentiate that and set the s equal to 0, then that result will give us this result, which will be a check. And then that will have been obtained without using Little's theorem. And also, it will show, though, well, let me say this. It will show that in terms of the total distribution, the Q discipline, that is the order of selection of service, is important, whereas we showed that in terms of the average, it's not important. That's what I just argued. But now to get the total distribution, I'm going to have to explicitly use the fact that the customers are served in the order of their arrival. And then, incredibly, we'll actually be able to invert that transform and get a closed form solution for the distribution function of waiting times. So that's what I want to do today. All right, so I'm starting in the text around page 216. Okay, so here's what I'm going to show. So I will show this. Or I hope to. That's the program here. First of all, I'm going to define omega of s to be the Laplace-Dirichlet transform of the distribution function of waiting times, which I'll call dw of t. I don't really like this notation anymore. I would rather have used capital F sub w, so I used F for all distribution functions. But this is the way it's done in the textbook. So w of t is a distribution function of waiting times, and we're going to assume FIFO, which means first in, first out, or service in order of arrival. So what I'm going to do is I'm going to define this and then show that omega, in this case, is given by the following expression. S times 1 minus rho divided by S minus lambda times 1 minus eta of S. And this is equation 837 in the text. And this is the famous Polytek-Kinchin formula. It's the Laplace-Dirichlet transform of the distribution function of waiting times in MG1 when the service is FIFO, first in, first out. So this is called Polytek-Kinchin. Although sometimes these other formulas that are mean value formulas are also called Polytek-Kinchin formulas. So if you believe that this is true, then if I took that thing, differentiated it, set s equal to 0, and multiplied by -1, then that would in fact give me this. And you could leave that as an exercise. Okay? Just arithmetic to do that work. Okay, then finally, well, let me first get this, and then I'll go back, and then I will try and invert that later. Okay, so first I'm going to make the argument about how I get this. Okay, so let me go back over here and recognize that we have this g of z. And the argument I'm going to give now is very clever and is due to Kendall. Okay, so what I'm going to write down is due to Kendall, who kind of, in a sense, took queuing theory and made it so that people who were a level below Polytek and Kinchin could figure out what's going on. So Kendall greatly simplified queuing theory by applying this tool of the embedded Markov chain and by making this clever argument that I'm going to make in a moment. So what we have here is we have the generating function of these pi j stars. Now, this is the distribution of the number left behind by a departing customer. Okay, so what happens is a customer arrives, and then he waits, and then he enters service, and then he has a service time, and then he leaves. So the time from arrival to departure is called his sojourn time. S-O-J-O-U-R-N. Sojourn time. Now, by assumption, because we have MG1, Poisson arrivals, we know that during the sojourn time of the customer, we'll take a particular customer that we'll call the test customer, and we know that during his sojourn time, other customers are arriving. And those customers, even though I didn't draw it that way, I should have maybe put in some bunching here. Those customers are arriving according to a Poisson process, by assumption. Now, if we have FIFO service, then when the test customer leaves, every customer that he leaves behind him must have arrived during his sojourn time. And every customer who arrived before him has already left. So if the customer leaves behind J, then we know that those J must have arrived according to a Poisson process during this sojourn time. So we have the same relationship that we had here. Here we had the generating function of the number that arrived during a service time, and the Laplace-Dirichlet transform of the distribution function of the length of the service time, as long as these customers here arrive according to a Poisson process. Okay, now we have the same thing. Now we have the generating function of the number of customers left behind by a departure. So that should be related to the Laplace-Dirichlet transform of the sojourn time in the same way. So if the sojourn time has Laplace-Dirichlet transform phi, then the generating function that we just found must be equal to that transform evaluated at lambda minus lambda z, where lambda is the arrival rate of the Poisson process and z is the dummy variable. Now, we also know that the sojourn time is the sum of two pieces. One is the waiting time, and the other is the service time, and those are independent of each other. So therefore, since these two things are independent, then the transform of their sum is the product of their transforms. The transform of W, by definition, is eta. So there's eta evaluated at lambda minus lambda z. And the transform of the service time, by definition, is what we called excuse me, I just made a mistake. It's not eta, it's omega. Omega, by definition, is the name of the transform of the waiting time. And eta, by definition, is the name of the transform of the service times. So since the sojourn time is the sum of the waiting time and the service time, therefore its transform is the product of their transforms. So now I can equate this thing to g of z, which is this thing. Those things are equal. So I can cancel out the eta, and I have an expression for omega of lambda minus lambda z. There it is. Now if I simply set lambda minus lambda z equal s, so now I will let lambda minus lambda z equal s and plug that back into here, the end result is exactly that. So that proves the Polytek-Khinchin transform. So when you think about it, it's truly amazing now that we started out by writing equations that determined the probability that at a departure instant, the number left behind by a departure was j. And we were able now to translate that information into the Laplace-Dieltjes transform of the length of time that an arbitrary customer waits for service. Okay, so is this clever or what? Okay, so this formula was originally derived by Polytek and Khinchin in the 30s, 1930, 1932. And re-derived by this argument, which is much simpler than Polytek and Khinchin's argument, in the 50s. So the formula was around for, say, 25 years before a simplified derivation was available. But still, if I have the transform, then of course I can get the moments, like the expected value and the variance and so forth, by differentiating. But what I would like is I would like to be able to get the whole distribution. To get the whole distribution, in principle, that's easy, in principle. Because all I do is you give me an h, from that I calculate the eta, then I put the eta in this formula, so I have something explicit now, and then I go backwards. That is, I invert. That is, I find the w whose transform is whatever this expression is for the given eta. Now, in electrical engineering, there are lots of techniques that people use for doing things like this, but they work for simple cases or for cases that happen to appear in electrical engineering. It's not clear that there would be a general formula that would give you the inverse of this. And yet, as I'll show you in a minute, there is. And this formula was found by Benish, B-E-N-E-S. And he found this formula in, I believe it was 57. Maybe it was 55 or something like that. It says in the textbook. Does anybody remember reading it? Well, we'll find out in a moment. 57. 57 is what I have written here. Okay, now what Benish found was the following formula, which is given in a text as equation 840. Okay, so here's what Benish found at 57. He found that, let's call W of t the waiting time distribution function. Well, just as we did here. So now we're going to go backwards and say, okay, what I'm going to do is I'm going to give an explicit formula for the W in terms of the eta. So here's Benish's formula. It's equal to, I'll write it slightly differently from the way it's written in the book. You'll see why in a moment. 1 minus rho, rho to the j, h squiggle, star j t as j runs from 0 to infinity, and this is equation 840, where h squiggle of t is equal to 1 over tau. Tau is the average service time. Integral from 0 to t of 1 minus the service time distribution function evaluated at z dc, and that's equation 841. Okay, so Benish's inversion says, okay, here's a transform. Now, here's the inverse of this transform. What he says is, okay, you give me the service time distribution function, I put it in this formula, and I get something else. And in fact, you recognize this as a forward recurrence time. So if I had a renewal process in which the times between renewals were the service times, then the h with the tilde on it represents the distribution function of an interrupted service time, the forward recurrence time, and also the backward recurrence time of an interrupted service time. Now, what this formula says is, okay, take that h tilde, and take its j-fold convolution, and multiply it by 1 minus rho to the j, and sum, and that will give you the explicit answer for w of t. Now that's amazing. It's amazing that, well, it's amazing for several reasons. One thing is it's amazing that you actually have a solution. Another is it's so simple, and yet it's complicated. Because, and this piece here, this is even the most amazing part, is that why does this piece arise? This, of course, is the full version of this piece right here. It's that forward recurrence time part, except it's the distribution function of forward recurrence time. Now, we went through an argument that was intuitive and that allowed us to calculate this by taking in the account in the intuitive argument that when a customer arrived, his waiting time was the sum of pieces, one of which was the partial service time that he interrupted. Okay, so I want to do something like that here. I want to go through the argument. First, I want to go through the argument that Benish went through to get this, which is actually very simple. Although it's interesting that it took 25 years for this to happen, because the formula was discovered in the 30s, and it wasn't until the mid-50s, 25 years later, that somebody came up with a general formula that inverts it. And then, another 25 years after that, somebody discovered why it works. And so that's also what I want to do. Okay, so does everybody see what the question is at this moment? All right, so the first thing I'm going to do is prove that Benish's result is right. And it's very simple, actually. It's just a matter of thinking the right way. In 57, I think that was a real insight, but nowadays everybody understands this kind of stuff. So you're always looking for these kind of things.
Have we defined the edge function hamper?
Say that again?
The definition of edge function.
This h is the distribution function of service times. So this is given. Okay, so first of all, let me remind you, equation 7.9 in the text was this. We said that if we had a renewal process, that the distribution function of the forward recurrence time, I'll denote that by this tilde, just like here. If we had a renewal process, and the distribution of the forward recurrence time was given by 1 over beta, where beta is the average time between renewals, integral 0 to t, 1 minus f of x dx, where f is the distribution function of the renewals. In other words, if I have a renewal process in which the inter-event times, the intervals, have distribution function f, then the distribution function of the forward recurrence time defined by or denoted by the same f with the tilde over it is given by this formula. And then similarly, equation 710, okay, so we derived that. That's the, we derived that using the key renewal theorem. And then, suppose I took the transform of this. Well, if I define the transform of f tilde as phi tilde, and the transform of f is phi, then I get this result. 1 over beta, 1 minus phi of s divided by s. Okay, so if I take transforms of both sides of 7,9, I get 7,10, and I did that in class. So I'm just writing this down to remind you that we have these results. So what that means now is that if I have a transform that looks like this, I can invert it by recognizing that it must be the transform of a forward recurrence time. Because I know that these things are going to come up all the time in queuing theory. All right, so here's the way I'm going to prove this. Here's the Polytek-Hintschen formula. It says that omega of s is equal to s times 1 minus rho divided by s minus lambda times 1 minus eta of s. Okay, that's what we have over here. So that's 837. And now I'm just going to rewrite that as follows. I'll take out the 1 minus rho. And then I'll divide numerator and denominator by s. So that's going to give me, in the numerator, 1. The denominator, when I divide by s, I have a 1 minus lambda 1 minus eta of s over s. Okay, well, that's starting to look a lot like this. There's the 1 minus eta of s over s. What I need to get is a beta in here. And I have to divide by the expected value. So what I'll do is I'll multiply by tau and divide by tau inside the parentheses. And of course, that piece is just what we've called rho. And so now I have omega is equal to 1 minus rho times 1 over 1 minus something. And the something is rho times this piece. And that piece is, in fact, well, let me write it again. What I have left is 1 minus rho times 1 over 1 minus rho times eta tilde of s. Because this piece right here is recognized as the Laplace-Dirichlet transform of the forward recurrence time of a renewal process whose renewal intervals have the are distributed like the surface times, because that thing is of the same form as that thing. So I'm going to call it that. And now I apply some ordinary high school arithmetic. I say, well, I have 1 over 1 minus something, and so I'll expand that as a power series. So what I'm going to get is the sum of 1 minus rho. I'll put the 1 minus rho inside the sum. And then when I expand this piece, I'm going to wind up with rho times eta tilde of s raised to the j power. So this expansion right here, this equal sign here, is just a geometric series. Of course, I have to justify that by saying that the thing that's being raised to the power in absolute value is always less than 1. But of course, rho is, and it can be shown that a Laplace-Dirichlet transform is less than or equal to 1. It'll be 1 only when s is 0. So the arithmetic is legitimate. Okay, so now what I have to do is I have to invert, because what we know is that omega is given by this, but now I can invert it term by term. So I say, okay, if I invert the left-hand side, then by definition, that's W. If I invert the right-hand side, well, now I have to apply a theorem that says that if I have an infinite series, the inverse of the series is the inverse of the sum is the sum of the inverses. Nobody would doubt that, although I have to prove that something about uniform convergence or that kind of stuff. But that's analysis and is irrelevant for our purposes because, for one thing, the strategy is, well, first you do it, and then if you get the result you want, get something worthwhile, then you go back and justify the steps. But you don't worry about justifying the steps before you care about them. And then once you get to justifying the steps, then that's just analysis. It has really nothing to do with this. And you know it's going to work anyhow because in queuing theory, all of the functions involved are all well behaved. They're all non-negative numbers between 0 and 1, so everything is nice. Okay, so what do I get? Well, when I invert this term by term, I get the summation as j runs from 0 to infinity. The 1 minus rho is a constant. I'll factor out the rho to the j. And now I want to find the inverse of omega hat to the j, eta hat to the j. Okay, now this is a transform. So if I raise it to the jth power, then we know that the transform of a convolution, or a sum, is equal to the product of the transforms. So that means that whatever eta hat is the transform of, if I'm raising the transform to the jth power, when I invert it, I'm going to get the j-fold self-convolution. So the first thing I do is I ask, what is eta hat the transform of? And the answer is, well, eta hat, by this formula, that is recognizing that that's the same as this form, okay? Eta hat is the same as h hat. So there's the h hat if I inverted that transform. But it's that transform raised to the j power, which means that this is the transform of this thing convoluted with itself j times. And of course, the result that I'm getting is exactly equation 840. In other words, if I took the transform of this, then I would get the transform of that. The transform of this j-fold convolution is the transform of h tilde raised to the j power. Well, there it is. There's a transform of h tilde raised to the j power. Okay, so what is this h tilde? Well, that h tilde is apparently the distribution function of the forward recurrence time of the surface time. So we proved Benish's result, the way Benish proved it. Basically, it was just by recognizing that if you take the Polytek-Khinchin formula and expand it, or actually you take the Polytek-Khinchin formula and you write it this way, you recognize that this piece right here is the transform of a forward recurrence time. And then the rest of it is simple. Okay, so now we have this result, but now this is very strange, because what does this mean? I mean, it means that, although it may not be practical, it means that if you tell me what the service time is, then I have an explicit formula for the waiting times, because all I got to do is take the service time, put it in here. Now, this may be difficult, because I have to calculate the convolutions. But in principle, it's straightforward. There's nothing implicit here. It's all explicit. Now, this raises an interesting question, because you say, here's the question. Well, before I go on to the question, are there any questions about this before I go on to the interpretation? Because, remember, we went through all of this algebra, and we come out with this answer. And the answer just seems to work because we just recognize certain things. And when you get done, you get an answer that's very simple. It's got these simple terms in it right here, and it's got this simple stuff right here. And so there ought to be a way of interpreting this term by term and saying what each term is and getting the answer. And everybody recognized that that should be true, because they say, well, this looks familiar, that looks familiar, so why shouldn't the sum of those things be meaningful? But nobody could figure out an answer for another 25 years. Okay, any questions at this stage? Okay, so let me get rid of the Polytek-Kinchin formula here. And let me see if I can answer the question as to what all this means. Now, you'll note that in the book, on page 219, there's a paragraph. Let me read it. It says, the rather mysterious appearance of the function h tilde in 840 is noteworthy. One can interpret h tilde as the distribution function of the elapsed time from the arrival of a customer until the end of the service time of the customer, if any, in service when he arrives. We've already done that. In the case of exponential service times, h tilde and h are the same by the Markov property. And then this yields easily to a term-by-term interpretation. But if you don't have exponential service times, then it doesn't seem to yield easily to this term-by-term interpretation. And the textbook says this provides a dramatic counterexample to the folk theorem, often true that simple results have simple explanations. But actually, simple results do have simple explanations, because I'm going to give a simple explanation in a minute. The only thing is that even though it's simple, well, it's both simple and complicated. After you know it, it's simple, but it took 25 years for people to see that it was simple. Now, there was a paper written about this particular derivation of this, although the original interpretation is not my own. This paper was written by myself and Shun-Chen Nu. I'll give you the reference, and then I'll outline that paper, which is the explanation of this right here. Okay, so the paper is by Cooper and Nu. Nu is N-I-U. And he and I have been working since around 1985 or so together. And we have an NSF grant together, and working with another guy named Srinivasan as well. And we're working on these kinds of models in a more complicated context, polling models and vacation models, and we'll lead into that. That's where we're going in the course. But in this paper, the title of the paper was Benish's Formula for MG1 Fifo Explained by Pre-Emptive Resume LIFO. And it appeared in the Journal of Applied Probability, volume 23, which was 1986. That's about 10 years now. Time flies. And it was on pages 550 to 554, if anybody wants to look it up. And our paper goes like this. We start out with this equation, which in the paper we call equation 1. And equation 2 is simply the statement that says what h of t is, or h tilde. H tilde of t is equal to the integral 1 over tau, integral from 0 to t of 1 minus h of x dx, where h is the distribution function of service times. So that's just this result right over here. Okay, so what we do in the paper is we start off and say, this is the result where this particular thing is defined that way, and now what we want to do is we want to explain what's going on. Now, we also know, so let's see, equation 3. I think I'll put it up here, because equation 3 is equivalent to that. Equation 3 says eta tilde of s. Let's recognize that that thing is equal to 1 over tau, 1 minus eta of s over s. Okay, that is the Laplace-Filter transform of that is that. Which, of course, is the same thing as saying that the Laplace-Filter transform of that is that. Okay, now, our objective is to explain why it is we have these terms. So first of all, let me explain why it's interesting, why we should ask that. Suppose that I simply used the theorem of total probability. To calculate the probability that the waiting time is less than or equal to t. That's what W of t is, a distribution function. It's the probability the waiting time is less than or equal to t. So the way you would do that is you'd say, well, that would be the probability that the number found by the arriving customer is equal to j times the probability that the waiting time is less than or equal to t, given that the test customer finds j, summed over all j from 0 to infinity. Okay, that's always true. It just may not be useful, but it's always true. Now, suppose that we have MM1. For MM1, the probability that the number found by the arriving customer is j, that probability is 1 minus rho to the j. In other words, if I write the rate up equals rate down equations for one server and get the p's, of course, are equal to the pi's, then this is the answer that I would get. This is the geometric distribution, and it's the simple result that everybody knows that describes MM1. Okay, so for MM1, this piece is this piece, if MM1. But if it's not MM1, then that piece is not that piece. It's always true that no matter what the distributions involved is, that this formula on the right is always valid. It's just that what we have is we have a formula in which this piece is explicitly that piece, and of course, this piece is explicitly that piece. I'll write it down here. The probability that W is less than or equal to t, given n is equal to j. All right, now why is that? This is very strong. This is the Markov property. That's equal to h tilde star j of t. Okay, now why is this in MM1? In MM1, here's the server, here's the queue. The test customer arrives, and let's say that he finds in front of him j other customers. Finds some people on the queue and the server busy, j other customers. Okay, now how long does he wait? He has to wait for the complete service time of each of the j customers in front of him, and those are the j minus 1 customers on the queue and the 1 customer in service. When he arrives, he interrupts the customer in service. So he has to wait only the remaining service time of the customer in service. But the remaining service time of an interrupted customer in service is the same as a full service time if the service times are exponentially distributed. So by the Markov property, in the case of MM1, then the sum of these j pieces, which is j minus 1 full service times and 1 partial service time, is exactly the same as j full service times or j partial service times. Because for MM1, as long as I have exponential service times, a partial service time and a full service time have the same distribution. So if I have MM1, then this piece is equal to that, this piece is equal to that, and in that case, we're home free. The problem is solved. And in fact, when we studied the MMS, and then we did it for MMS, but of course we could have specialized to MM1, this is exactly the way we did it. We calculated the state probabilities, we calculated the probability of waiting longer than t given the number of customers in front of you, and using the Markov property, we were able to get an explicit expression for that. And then we just carried out this, it turned out it was a double sum, and we got the well-known answer. Okay, so for MM1, there's no problem here. It's clear that this is the right answer. However, in general, if we don't have exponential service times, this piece is not that piece, and this piece is not that piece, but nevertheless, if I take those pieces, multiply them together and sum, I still get the right answer. So why should that be? Okay, that's the question. Okay, now the answer was figured out by Kelly in his book. Let's see, do I have the date here? I believe it was the late 70s or so. Okay, it's written down here, but I can't find it. Let's see. Kelly, 79. Okay, you should start getting familiar with the literature. But Frank Kelly is one of the major contributors to the field, and he wrote a book called Reversibility and Stochastic Networks, a Wiley book published in 1979. And in that book, he had this explanation. And the explanation is, he says, instead of looking at MG1 Fifo, let's look at another model. So what we've been looking at so far is MG1 Fifo. Kelly says, let's look at another model, which at first glance doesn't look anything like it, which is MG1 LIFO, preemptive resume. And let's look at remaining work in that model. All right, now the strategy is, it turns out that the waiting times in MG1 Fifo and the remaining work in MG1 LIFO preemptive resume have the same distribution. But it's easier to calculate this one than it is to calculate this one. So Kelly's contribution was to show that they were the same and then come up with a complicated way of calculating this one. And what we did in our paper, Cooper and New, is we came up with a simple way of calculating this one. And so that, or at least simple, unless you're extremely rigorous. But I'll give you the argument. I think you'll find it convincing, and then that will give us a simple derivation of this. All right, so first of all, let me explain the relationship between MG1 Fifo and MG1 LIFO. Now, LIFO preemptive resume, what that means is the following. That means that, here's the queue. Customers arrive. When a customer arrives, he immediately enters the server, and he begins his service time. If nobody else arrives, he leaves. If somebody else arrives while he's in service, then that person bumps him, and he moves to the first position in the queue, and the new arrival takes the server. And then if another customer arrives, he enters the server. This guy moves to here, this guy moves to here, and so on. Now, if we have a queue here, and then somebody in service leaves, then somebody who was on the queue, the first person on the queue, moves back in and resumes his service where it left off. And then if another customer arrives, he could be bumped back, and so on. So the effect of this is that from the viewpoint of the arriving customer, the customers who are ahead of him are transparent. What he does is he immediately enters service so that his service time, so that his waiting time is 0. If he's lucky enough to get his complete service before somebody else arrives, then he's getting very good service. On the other hand, if he's unlucky and he gets bumped, then he has to spend time waiting in the queue, then he comes back, then he might get bumped again, and he might be pushed further back, and so on. So what you see here is that Customers whose service times are short tend to get good service because they immediately enter service and they get out before somebody pushes them back. But customers whose service times are long are going to be moved back and forth, and it may take them longer to get their service time. So these two models are of interest, comparison, just because there are two different Q disciplines, and it's not clear which one is better. It may be, for example, that in this case, short service, it's better for short service time customers and worse for long service time customers, but what on average, it could be worse, it could be better, it could be the same. That depends. And that's one of the things we want to investigate. Okay, so the relationship between the FIFO and the LIFO preemptive resume, should be a T in here, preemptive resume, is in itself interesting. Okay, so in the name here, LIFO means last in, first out. That says that the arriving customer immediately enters service, so the service order is reversed. Preemptive means that when the customer arrives, he doesn't go here in the queue, he goes immediately into the server and preempts the previous customer. And resume means that when he re-enters service, his service begins from where it left off, as opposed to, say, starting again. Okay, so that's what the name means. Okay, now suppose we have MG1 LIFO preemptive resume. Now I'm going to look at what's called the busy period. And I'm going to plot here the remaining work as a function of time. This is what's called a sample path, an example. So suppose a customer arrives and he finds a server idle. Then the remaining work is the amount of work, by definition, that it takes until the server becomes idle if there were no new arrivals. So at the instant the test customer or this first customer arrives, the remaining work jumps, and the amount of the jump is the service time of that customer. And then the remaining work decreases linearly with time. That is, 1 minute of time, the amount of remaining work decreases by 1 minute. So the server is working off this backlog until another customer arrives. And as soon as that other customer arrives, the graph jumps up by that customer's service time, and so on. So you get a picture that looks like this, in which you've got these jagged edges, this saw blade, in which the jumps up occur at the random Poisson arrival points. The height of the jump is the service time of the arriving customer, and in between jumps, the curve decreases with slope -1 until eventually it crosses 0, and that means that the server is idle, and then the process starts again later with the next arrival, and so on like that. Okay, so that's the remaining work. Now notice that the remaining work would be the same in both models, because it really doesn't matter, I shouldn't say really doesn't matter, it doesn't matter in terms of the amount of work whether or not the customer brings in his work and goes into the server and displaces somebody who's there or goes to the end of the queue. The total amount of work that remains to be done is not affected by the order in which you serve the individual customers. So therefore, remaining work is invariant with respect to Q discipline. So if I plot remaining work, it's the same in both models. Okay, now let's look at waiting time in the FIFO model. If I look at waiting time in the FIFO model, then let's say I look at a customer when he arrives. Here's a customer when he arrives. When he arrives, the remaining work at his arrival time is the graph just before the jump. Now, how long does this customer have to wait? Well, if it's FIFO service, then he goes to the end of the queue, and he has to wait until all the remaining work in front of him is finished. So therefore, the waiting time for a FIFO customer is the same as the remaining work in either model. And therefore, if I can calculate the distribution of remaining work in MG1 LIFO preemptive resume, the answer that I get will be the same as the waiting time in MG1 FIFO for the model that's otherwise the same. In other words, the same arrival process, same service times. Okay? This is the key insight, and now the rest of it is to make the calculation. But it's going to turn out that the calculation for this, if I calculate remaining work, is much easier and gives me this answer almost immediately. That's what I got to do next. When I say almost immediately, that's actually a big jump. Okay, so are there any questions about this? Maybe I should repeat this because we only have a few minutes and I don't have enough time to do the rest of the argument. Okay, so let me repeat this and I'll start from here next time. Before I do that, are there any specific questions about this? Okay, so the big, yes.
When you're talking about the FIFO,
About the what?
FIFO, in the FIFO model,
FIFO.
is the service time independent of the arrival time distribution?
The service times are, and the inter-arrival times are independent, yes.
How can they independent? Since you have a guarantee that the first in, first out.
Well, they're independent in this sense. Whenever a customer arrives, he picks his service time from a service time distribution, a population, and that choice is made without regard to anything else. It has nothing to do with the past history. It has nothing to do with the absolute time. If I were to simulate it, I have this urn, and in it I have these service times. And when a customer arrives, he just picks a number out of here. And it's the same in both models. He picks from the same urn. The only difference is that in this model, he joins the end of the queue. And in this model, he enters the server immediately.
For instance, if one customer arrives, his service time certainly related to the histories. Otherwise, you cannot guarantee first in, first out.
The service time is the amount of service that's required.
Yes.
Okay, so here's the server.
For constant, certainly you can guarantee FIFO.
By service time, I mean the length of service. I don't mean the time at which the service occurs. So when a customer arrives, let's say the system is empty. A customer arrives, he reaches into the urn, he pulls out a number. That's his service time. He enters the server, and the server is busy that length of time. Now, another customer arrives, let's say he's still in service. That customer pulls his service time out and joins the queue. And then another customer arrives, and so on. Now, each of these customers has reached into the urn and pulled out his service time. So when he enters, the length of time he waits depends on the past history. But the length of time that he actually spends in service does not depend on the past history. Okay? Now that's the same no matter which model I'm in. The only difference is that in the first model, when a new customer arrives, he joins the end of the queue. In the second model, when a new customer arrives, he enters service immediately and he pushes everybody in the queue back one position.
Since this is MT1, how about MT2? Can you guarantee?
How about
MT2?
MG2?
MM2. Since you
No, with MG2, as soon as you have two servers, then things become much more complicated in the sense that with two servers, service and order of arrival is not first in, first out necessarily, because if I have two servers, then this guy could enter here, and the next guy could enter here, but he could come out sooner.
Yes.
Okay, so sometimes these systems are called systems which are overtake free, or systems in which one customer cannot pass another customer. So in the case of single server, you have that property, and that's critical because that keeps everybody in a nice order. And in fact, that was necessary for Kendall's argument that says that when a customer leaves, the customers he leaves behind him are exactly those customers who arrived during his sojourn time. Otherwise, if a customer could overtake him, then maybe a customer he leaves behind him, maybe a customer who arrived later leave sooner, and so on. Okay, so this is an important assumption. Simplifies things a lot. That's why 2 servers are much more difficult than 1 server for these kinds of questions. Okay. Okay, so that was a good question because now we're out of time. Okay, so it just fit right. So next time what I'm going to do is I'll review this, but the main point is that now we know that remaining work in this model and waiting time in this model are exactly the same. And then I'm going to analyze remaining work in this model and show directly that the answer that we get is exactly this answer. And I'll show some other things as well, some nice, interesting facts as well. Okay.